Hello and welcome to this installment of Mathematical Foundations in Physics. Today's topic is bias. And there's several different kinds of bias. The seminal experiences we have had so far in the course really are about the lab's linear measurement, and inclined plane. And in those labs, we've spoken at length about these different biases. So the bias itself is part of a larger question that we might ask, which is how do we ensure objectivity in our data? That is one of the essential elements of science, is trying to remain as objective as possible. However, we are humans, so we can never be truly objective, but we strive for it, and we strive to acknowledge and identify all places where we may not be objective. So bias falls under that realm. Now, bias appears in other disciplines, but we have specific meanings to it and occurrences for it in science. So let's just follow this general thought process. And the general thought process is this. First of all, analog measurements always result in random error. They always result in random error. And that is because they require human judgment. Human judgment required. The next thing we want to add here is that although multiple trials are required, trials cause new problems. So we have analog measurements. They result in random error. We do need multiple trials, and those new trials cause new problems, particularly problems of bias and experimental design. Memory bias occurs when one person takes multiple trials. So that's the first thing we need to realize. If we're in an experiment and we want to eliminate memory bias, the first thing we need to do is eliminate one person making multiple trials. And again, all of this conversation is about analog measurements, not digital. So zero bias occurs from indolence, which has been previously defined, but it does come from indolence. 0.5 bias also occurs from indolence. Anti-zero bias occurs from overcompensation. That's when you become aware of something and you work so hard not to be that thing that you overdo it. And anti-5 or anti-half bias occurs also from overcompensation. And what's interesting too, and this is important for us, is that we can detect all types of bias by looking at our data. Now, before we go further in this lesson, you want to make sure that you have viewed and have under your grasp the Mathematical Foundation 002 on uncertainty. That's really a prerequisite for the detail in this lesson. So uncertainty, or I guess I should say bias, that's a typo. For bias, the word I already mentioned before, indolence. It's the state of showing no real interest or effort. Some might say a synonym for it is laziness, but I think it's just really more about an inattentiveness that's a result of a lack of interest or a lack of effort to pay close attention. And from habits of mind, striving for accuracy, people who value truthfulness, accuracy, and precision, and craftsmanship take time. They review the rules which they're to abide and review the criteria and to make sure their product matches the criteria exactly. And so this whole element of data collection and how we communicate it and uncertainty is all about this striving for accuracy and requires additional effort. So another thought process for us to think about. Whenever we measure, there is uncertainty. It's unavoidable. It's ineluctable. And when it is analog, the uncertainty is random error. Now, the reason we're making measurements is we want the true value. And to get the true value, the best estimate of the true value is the mean. It requires multiple trials and the mean. And that's because if three people were to measure the same thing and they're doing an estimation, they should and are likely to end up with slightly different answers. So the question is, which one do we go with? And that was hashed out in 002 uncertainty. So whenever we measure, there's uncertainty. If we want to know the true value, we need the mean because that's the best estimate of the true value. To get an accurate mean, we need to take multiple trials. And when we have multiple trials, there are more potential for problems. And some of those are biased. That's the subject of this lesson today. So let's first talk about memory bias. That occurs when one person makes multiple trials of the same thing. Their memory of the prior measurement biases the placement or the reading of the next trial. So let us suppose we have an object that when we are lining it up on the ruler is that long. And we do make an estimate, a reading, excuse me, and we make a reading here and we can see, all right, here is 20, 21, 22. So there's 22. And since the ruler is measured in ones, we're going to estimate the tens place. And so let us suppose that we measure this and we say, okay, so there's 20, 22, and there is 23, and we're going to say this is 22.1. So a proper measurement might be 22.1. Well, we record that, and then we take this whatever this black line object is, and if it's still remaining in position, we look back down at the ruler, and because we remember it's 22.1, we say 22.1. We don't even put in the effort or the time to really judge whether it is 22.1 again. And moreover, if we are relining the object against the ruler, we will tend to line it up in exactly the same way. And even if it's in a very different place, because we remember, we will report 22.1 again. So the point there is that through inattentiveness, we will tend to report the same number over and over again, consciously or unconsciously. And that's what memory bias is. Now, how we can identify that in the data, it's usually fairly simple. The trials show very little or no variance. So the truth of the matter is that every measurement we make, we should expect to see a normal distribution, where the greatest frequency of measurement is about the mean. And so if we say this is the mean right here, and we say it's 22.1, then we might also expect 22.0s, 22.2s, 0.3s, and maybe even 0.4s. And as we get farther and farther from the true value, there become fewer and fewer measurements like that. But we should also experience a 21.9 and a 21.8 and a 21.7 in either direction. But if all we see is 22.1 over and over and over and over again, that's unlikely, because humans, whether it's the same person or different people, will judge the same thing, and there'll be variation around a mean value. So there's little or no variance. We get 22.1 every time. So what are the strategies we can use to eliminate that? The first one is we never have one person making all the trials. We have multiple persons do it. One person does not make multiple trials. We record the data blindly without seeing the list prior to the measurements. So we can undo our attempt to eliminate memory bias if we have someone who makes a measurement, writes it down, and then the next person goes and sees that measurement. They will be biased to give the same measurement. So we don't want people to be able to see that. So the next thing we do is we want that data to be recorded blindly. And there are other ways to do that too. One can have a form that you submit over and over again. The other way to do that, is to make other measurements or do other things before making another trial so that you have sufficient time to forget the prior measurement. So that is how we identify, that is what memory bias is and how we identify it and how we eliminate it. So now let's talk about zero bias. So in the last case here, we said that the object had a length of, say, 22.1. And when that's drawn, it comes out here like this. It's about that long. And that zero bias also comes from indolence. The problem there is that we have our 22.1 and it's close to the zero, 22.0. And so things up a few estimated increments and down a few estimated increments, we just round it. We simply round it to the zero. So those measurements that are near the zero mark, for example, 17, 18, 19, 21, 22, or 23, we would round to 0.20. We round them toward a zero value. And that's really the problem we experience there. And so how do we identify that? We identify that by there being a preponderance of zeros in the most precise or the rightmost decimal place. And so what this would look like in the data is if we have 22.0, 22.0, 22.0, 22.0, that is the zero bias, when in reality it may be a little larger. We don't see 22.1s or 22.2s or 19 or 21.9s or 21.8s. We only see the zeros, or mostly zeros, which suggests that however the measures are being taken, people are rounding it to the whole decimal. And remember, we expect that our data should follow a normal distribution. And so even things that are consistent and have a definite value, even if it were to be really zero, we would expect some measurements a little larger than that and smaller than that. And the fact that there are very few or none suggests that there is a bias toward rounding things to zero. So how do we eliminate that problem, you may ask? We should strive for precision by being skeptical of zeros. Whenever we want to write down zero, we should take pause and ask ourselves, are we guilty of zero bias here? And do a double take. And is this really on the zero? Is it more like a 1? Or is it really like a 9 of the smaller number? And the other key piece here is to remember that the measurements should be normally distributed about the mean. And that if I'm getting a 0 and there are other measurements that are also 0, something may be suspect. Now, it could happen that something is exactly 0, but the likelihood that all of those measurements taken objectively will be 0 is unlikely because humans are estimating. So that creates yet another problem, and that is an anti-zero bias. And the anti-zero bias happens when we overcompensate for zero bias. So I'm enlightened. I am woke when it comes to bias in my numbers. And I know that that number shouldn't necessarily be 0 all the time. So when I get a number and I am skeptical of the 0, when I intentionally change it so it's not 0, that's an anti-zero bias. So if we think it's 0, but we're reluctant to put a 0 lest we be accused of having a zero bias, we change it to something it's not really. We put it as a 0.9 or a 0.1 when it really is the 0. So how do we identify that as a problem? Is that there is a paucity of zeros, which means there are very few zeros in the most precise decimal place. And how that might manifest itself in the data, interestingly enough, is that if we look at the measurement, instead of it being a normal curve whose mean is, say, 22.0, we might get something that looks more like this. Aha! There are way fewer zeros than we expect. Why? Because people are avoiding them. We get what's called a bimodal distribution. So we want to look for that. Like, oh, there are lots of 22.1s and there's lots of 21.9s, but very few 22.0s. Now, that is odd because when we have enough trials, we would expect the actual value to have the greatest frequency. And when we look at that histogram, of course, it doesn't look normally distributed. So, strategies to eliminate anti-zero bias. Strive for precision by not being afraid. Don't be afraid to report the zero digit. And remember that they should be normally distributed around the mean. So we look to see, is this number seeming to make sense? Is it normally distributed around the mean? And that is zero bias. Now it is time, my friends, for the half or the 5 bias, as I may call it. Now let's suppose, so this problem also occurs for indolence. It's very much like the zero bias. We're going to be very heavily biased toward choosing things exactly on the zero. But what we've talked about previously is that humans are pretty good at judging the halfway mark between things. We're pretty good at judging the halfway mark. So in this case, we have the 24.5. And so what we have there is we have a bias for people who have measurements that are close to 24.5. And those would include measurements like 24.4, 24.3, 24.6, 24.7, and labeling them and listing them as 0.5 when they're not really. We're being kind of not putting in effort, and we are just rounding them to 0.5 because that's the easy thing to do rather than being precise in our judgment. So that's what the 5 bias is when we see a preponderance of 5s in there. And so, of course, as I just said a moment ago, that is due to indolence, and our human limitations around judging more finely than 1/2 or 0.5. We're good at 0.5, but not necessarily good at judging beyond that. And of course, it takes practice, but in general, that's the nature of the problem. So, how do we identify this problem? There is a preponderance of 5s in the most precise digit, and a lack of 5s of non-5s in the most precise decimal place. So how that manifests itself again, and how we see that, is that we expect if the real value is 0.5, that there would be variation around it. And as we got further and further away from that 0.5, there'd be fewer and fewer. But they wouldn't be all 0.5s. And we certainly wouldn't expect them to all be 0.5s and all zeros. If all my measurements are zeros and 0.5s, I've got not only a zero bias, I've got a 5 bias. And I've got some serious problems there because what that's going to do is increase my uncertainty. And I want to be as precise as possible. I want my plus or minus to be small. The smaller the better. The smaller, that makes the measurement more precise. And that's what we strive for. All right, so that's how we identify it. We have more 0.5s or exclusively 0.5s and no 4.6s, 4.7s, 4.4s, and 4.3s. And we should expect there to be fewer 4.7s than 4.6s and fewer 4.3s than 4.4s and so on, with the most frequent being the 0.5, but not solely 0.5. So we identify the preponderance by the 5s and the lack of or the paucity of non-5 digits. How do we eliminate the half bias? Well, we do it the same way we did the other. We want to be skeptical of 5s. Whenever we're going to write down and say it's 5, we want to double check ourselves. Is that really 5, or is it really just a hair more than the halfway mark, or is it a hair less? Is it really 0.6? Is it really 0.4? So we want to be skeptical. And again, this tool that keeps coming up is that we expect the measurements to follow a normal distribution. It should be normally distributed around the mean. And if the mean, which we believe is the best estimate of the true value, then the mean should be the most frequent. And as you go to larger numbers and smaller numbers, should be less and less, thus the normal distribution. And of course, you guessed it, there's an anti-5, an anti-half bias. And that again occurs because of overcompensation for 5 bias. When you are woke to 5 bias, there's a danger in being and overcompensating for that. So, and what that leads to is it leads to one avoiding a reading of exactly the 5 mark. And so how we identify that is a paucity of 5s in the rightmost decimal place. And the others are present. So how we drew this before is we said, well, we expect it to be a normal distribution. And if the value is really 5, then we would expect there to be fewer 6s and fewer 7s and fewer 4s and fewer 3s. But if I end up with a distribution that looks like this, that's a sign that I'm implementing 5 bias, because if 5 is really the true value, there should be the most there. And of course, by avoiding the 5, I get a bimodal distribution. So the strategies to alleviate, our strategies to alleviate is to not be afraid to report a 5-digit. So when you think it's a 5-digit, you don't want to over-report 5s, nor do you want to under-report 5s. So whenever you're going to get that 5 or the 0, you want to be doubly certain. Check over and over and over again. Is it exactly in the middle? Or is it a little bit more? Is it a little bit less? There's no right answer to that, except are you putting in the effort to judge correctly? And of course, as always, remember that they should be normally distributed around the mean. And that, my friends, is a summary of all the details of bias.